Hi everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation. We've got a brand new paper to talk about, and it comes from Andrew Jordan and Qiaofu Zhang at the University of Alabama. And it's all about thermodynamics-based hot cracking models for additively manufactured alloys. Now, if you're not familiar with hot cracking, it is a super common problem. Here you see some images of it. In the additive manufacturing process, it is very common for these cracks to form, and it ruins a bunch of your builds. And you don't see it until the end of the build, typically. So they point out that this is a major problem. They call it a fatal defect that severely limits the processability of different alloys. So we would love to be able to predict this ahead of time. And there's been a few out there. In fact, they talked about a couple different non-mechanical hot cracking models that are derived from this Scheele-Gulliver solidification curve. Now, what is that? They look a bit like this. As a function of temperature, what it's showing you is the fraction of solid, right? As you're going through from a liquid to a solid region, it's basically showing you the volume of the solid with the conceptual notion that hot cracking susceptibility is most severe during this crack vulnerable time where the last drip of liquid is present, compared to the thermal stress relief time. So that's the premise behind these models, and there's several to pick from, right? There's the OG model, Klein-Davies CSC model. That one goes way back to 1981, right, before I was around. But there's other ones like the HCS model right here, or Koh's CSI model, right? Several different ones to sort of pick from. And what the authors are setting out in this paper to ask is, hey, does one of these models actually work across all different model systems? Because if you're actually capturing the underlying physics, then it should work just as well on steel as it does on HEAs, on nickel superalloys, on aluminum, right, as other steels. But that hypothesis has never been tested. No one's actually done this sort of rigorous study. So they set out to do it here. They looked at 460 different alloys taken from 128 lit sources across these 5 different alloy families. And they did these Scheele-Gulliver calculations. They did the whole implementation of these hot cracking models. And then they assessed it against actual experimental data. So they went about collecting the data. It says here that they actually had to collect whether or not cracks were present. Sometimes it was just reported in the paper as a binary, like 0 or 1. And sometimes they actually provided the micrographs. And when they did, here the authors actually did the effort to use IMMI, where they actually measured the crack length and the crack density. And then using Thermocalc 2024A software, they were able to calculate the susceptibility of these different alloys to hot cracking. Their workflow looked something like this. You can see going from data to packaging and getting that data ready for the thermo calculations. Here they're actually doing those thermocalc calculations. They had to do a gradient-based steepness correction in some cases to get this adjusted delta T. Then they could feed it to the models and assess these hot cracking indices according to the different models. But the big question you should have is, how well did they perform? Well, I think it's best summed up in this table too, and the results are honestly pretty sobering. Across these 5 different alloy systems, aluminum, stainless steel, other steel, nickel, and high entropy alloys, what we see is sort of 2 observations. First, there is no one thermodynamic model that works perfectly across all of them. Well, that is like consistently better across all of them. CSI does well with aluminum, stainless steel, and high entropy alloys, but CSC does better with the nickel alloys, and the delta T model does better with the other steels. But the second takeaway that I get from this is that look at the average accuracy. It's not that great. It's in the range of, say, 50 to 70%. In other words, this is still an open problem that additive manufacturing is going to have to deal with. And I personally am excited about the different approaches that I'm sure we're going to see addressing this in the future. And I'm grateful that these authors have put together such a excellent, benchmark data set that I'm sure others will build on going forward. So read all about it in the latest issue of IMMI.